Now we are live. So welcome back to our lecture on differential and integral calculus. I'm going to talk about the series today. We are going towards power series, and then next week we'll cover some of the limits, like limits such as the limit to infinity of certain kind of functions and so forth. And we tie it down to this series, and we talk about what are called the Taylor and Maclaurin series a little bit. I'm not, we don't have the time constraints or the time window here. So what we would continue with our discussion, we would continue our discussion with would be proofs that in certain cases we can use the Taylor and Maclaurin series, which I hopefully will be able to talk about today, to demonstrate that every certain kind of differential equation with initial value problem for a given differential equation has a unique solution, and it always can be solved. And we could use, I mean, in certain situations we could use this Taylor polynomials and Taylor Maclaurin polynomials or Maclaurin series to prove that this exists. That theory goes a bit beyond what we discuss here, but I will still explain part of that theory, especially with the Taylor series. Should be familiar to some of you. Just hang on a second. I'll close the curtain because it's right. So last time we talked about sequences, and we're going to be moving just very quickly, talk about go through what we talked about. So sequence was basically, parameterized sequence, I ranges from 1 to n and then to infinity, and then n goes to infinity of numbers, basically, real numbers. And very often the case is that they are defined recursively, or they're just defined in some other way. And we can come up with a closed form solution for the nth element in the sequence. And we talked about the limit of a sequence. So the limit of a sequence, the sequence idea of a sequence is it never ends, but the limit is like we think that the sequence approaches certain number, maybe. And in some situations it does, and then we can look at them as a function approaching a certain value as its parameter approaches infinity. And we had this theorem just saying that if we can express this an with a continuous function, then we can describe the limit of the sequence as the limit of the function as x approaches infinity. We had these algebraic limit laws, like the limit of a constant series is a constant sequence which repeats one number only is that number. When you multiply all the elements of the sequence by c, well, the limit becomes multiplied by c. The sum of limits is the limit of sums. The product of limits is the limit of limit of the product is the product of limits, and the limit of the, if we divide the elements of one with the elements of the other, then it's the limit of a divided by limit of b, provided that none of these bn are 0. Obviously, if there is a 0 in between, then that sequence has numbers that are not defined, so it's ill-defined sequence. All right, and the definition of the limit was really important. It was very, very much the same as the limit of a function. So the idea is that a limit is L if you can get closer and closer to L, and once you pass some threshold, capital N, then all the numbers after that N in that sequence will be closer to epsilon closer to L than epsilon. So if for all epsilons we can find such a limit, then the limit is in fact L. We can classify certain sequences I talked about this continuous functions defined on convergence sequences. The limit is, you can take a function and that allows you to, so f of an, you know, the limit is of the function is limit of a series which has f of an is the f of the limit of an. If we're dealing with continuous functions. Sequence, we can say that it's bounded above if all the numbers in the sequence are smaller than or equal to some number. So obviously when a function is, when the series is convergent, then in fact it must be bounded because all the numbers have some, I mean, all the numbers will be smaller than or equal to something. Or larger than or equal to something. So the sequence is a bounded sequence if it's bounded from above and below. So every convergent series is bounded, but not all bounded series are, or sorry, bounded sequences are convergent. There's a fairly easy. An increasing sequence, again, just like an increasing function, an increasing sequence is or non-decreasing or strictly sequence or whatever. The same apply as functions, so that if the next one is always is never smaller than the previous one, then we say it's increasing. And again, it's strictly increasing if they're all strictly larger. And decreasing, the same thing. For instance, the sequence where an is 1 over n is decreasing, and it's even strictly decreasing. All the numbers in that sequence are smaller than or equal to the previous one. So if we have a bounded sequence that is monotone, then so that it's either, if we have a bounded sequence that's either increasing or decreasing from some point onwards, then that function, that sequence will be convergent. Why? Well, let's give a intuition about this. We have a limit. No number in the sequence is greater than that limit. I can draw a picture. I'll draw you a picture. So we have here, you know, let's draw this. You know, we have 1, 2, and so forth. And then let's say there's a limit, okay? There's that limit. And it's bounded from both below and above, but, you know, it doesn't matter what. So this is the bound, and all the numbers are smaller than this. And bounded, you know, it may be bounded from below as well. Let's say there's a lower bound, which I draw here. So this is the m, and this is the m plus, m minus. So we have two bounds here. We have the upper and the lower bound. The lower bound is here. That's 0. And then the sequence is, you know, monotone from some point onwards. Let's say from that point onwards. So we have some point, and it's increasing. So let's say that it's increasing. I'm going to just draw it like this. So the numbers in the sequence increase. We know it will never pass this number here. This may not be the limit, but the limit is somewhere below here because, you know, if it's bounded, it will not go above that line, and because it's monotone, it cannot return back downwards. So if the only way is upwards, it must approach some number that is smaller than that upper bound. It says here the proof is beyond the scope of this text. The reason why the proof is beyond the scope of this text, it really requires more than this hand-waving intuition. It requires all these kind of things called completeness, which says that there are no holes in the real number line, and you know that goes beyond this particular course. But the intuition is such that if you're increasing and you know there's a limit you cannot cross, then there must be a limit that you approach, because you can't go back down, you know. There's here are some examples of a situation where you can use the monotone convergence theorem. You have 4 to the power of n over n over n factorial. So we notice that once n passes 4, the terms start decreasing. And because it's decreasing sequence and we know that it's bounded, it cannot be smaller than 0, then this must have some kind of a limit, right? So 4 to the n divided by n factorial. So from n equal 4 onwards, all the numbers are smaller than the previous one. And these are positive numbers, then it definitely must be a convergence theorem. We don't know what that limit is, but it must be convergent because it's a decreasing. Well, we actually can find out that it's actually 0, but yeah, we're not going to go through this example. You should go through this. You should really be careful to make sure you understand this, or if not understand, then memorize it, that the bounded sequence that is monotone. So if it's increasing or decreasing and it's bounded, then it's going to be convergent. So here's a sequence that is recursively defined such that a1 is 1 and an is always the an minus 1 divided by 2. So use the monotone convergence theorem to show that this sequence converges and find its limit. Well, let's do this together. There are 11 of you. First of all, A1 is positive. How do you determine that all the numbers in this sequence are positive? Anyone can answer. Look, A1 is 1, and the next one is always gained by taking the previous one and dividing it by 2. So I'm just going to claim that all these numbers are positive. All of these numbers are going to be greater than 0. Why? Well, we can prove this by induction, can't we? The first number is positive, obviously. If you take a positive number and you divide it by 2, the result is going to be positive. So that's actually an inductive proof that all of these numbers in this sequence are positive. So it has a lower bound at 0. Also, if you have a positive number and you divide it by 2, the result is smaller than the previous number, right? So this is a decreasing number, a decreasing sequence, and it's bounded by below. So obviously, it's also bounded above by 1. So all these numbers are between 1 and 0. It's a monotone sequence, so it's going to be converged. So when it's converging, what is its limit? Well, it's decreasing, so actually you can solve this, and it's going to be, an is going to be 1 over 2 to the n minus 1, actually. So as n approaches infinity, it's going to be 0. Here's a student project which I want you guys to look at. That's the so-called Fibonacci sequence. You may or may not want to do this. The first Fibonacci sequences well, it's a fascinating thing. Fibonacci sequences appear a lot in the nature. You can think of this process whereby you start with 2 individuals, 1 and 1, and then you add. You always come up with a situation where you have a population at time n minus 1 and the population at n minus 2, and then the population at time n is the sum of those two. So this results in what is known as the golden ratio. You can check it out. You can check out that if you look at the limit of the ratio between consecutive Fibonacci numbers, then it's going to have a solution where it's where their quotient is 1 plus the square root of 5 over 2. And this is known as the so-called golden ratio. Well, actually, yeah. Not going to go in depth into this. This number pops up in many places, but yeah, it's actually a nice project to do this, but we're not going to do it now. The ancient Greeks really appreciated this, and so they built a lot of stuff using golden ratios. And a lot of the, it's for reasons that are not completely understood, the aspect ratio of many paintings and so forth is aesthetically pleasing towards the eye if it's in the golden ratio. So these exercises, a lot of these are going to be in the next exercises, as are going to be the discussion about infinite series. So the difference between a sequence and a series is that a sequence is just a list of numbers, but a series can always be broken down to a sequence of numbers that are then added together. So an infinite series, we think of it as a sum of numbers, an infinite number of numbers, a sequence of infinite numbers, we add them all together. But this makes no sense, obviously. We can't have an infinite sum. We can't add an infinitely many numbers together. Not as such. But what we can do is really, we can take any beginning part of that sequence or that series. Now we call it a series. So we add k of the first numbers in that sequence. Look, there are two things. There is the sequence, which contains the numbers A1, A2, A3, and so forth. It contains an infinite number of numbers. That's a sequence. A series is when you try to add these together. And in that series, we can say that the kth element is, in fact, adding the numbers from A1, A2, and so forth, all the way to AK together. And then we look at the limit as k approaches infinity. So here are some examples that we can look at. Remember I mentioned this so-called Zeno paradox. The Zeno paradox was that if you shoot an arrow towards a target, then it will never reach it, because it first has to reach halfway between you and that target. And then when it's there, it needs to reach halfway between that point and the target, and so forth. So it has an infinite number of these steps to traverse, so it's never going to reach its target. So what happens here? What happens in infinity? So here's one idea of how to solve this infinite sequence. So we suppose there is this oil example. Okay, 1,000 gallons enters the lake. First week, the second week, 500, then 250. It's always the half of what was before. So first there's, we add these amounts together. So first we divide this by 1,000. So first there's 1, then there's 1 plus 1/2, then there's 1 plus 1/2 plus 1/4, and so forth. So you get this infinite sequence. If you continue this to infinity, kth element of that is the sum of the 1/2 to the power of n minus 1, where n ranges from 1 to k. So what is this? What is this sum as k ranges to infinity? Well, we know, many of you already know how to solve this. I'm going to show how you solve this this so-called geometric series. Now we talk about series, not sequence. Sequence is the sequence of numbers. Series is the sum. So let's call this sk, and we're actually looking for the limit as k approaches infinity of this sk. So there are some calculations here, and it has been concluded here that it approaches 2. Well, that kind of numerical trial and error, it doesn't prove anything really. So I'm not a big fan of teaching this to you. Sorry that I'm yawning. I'm tired again. So I would rather have this taught in a different way. But let's look at this first. So an infinite series is basically the limit of this partial sums. So we have a partial sum, it's the first k element, and we can form these partial sums into a sequence. And that sequence, you know, the k ranges 1, 2, 3, 4, so forth, all the way, you know, for all natural numbers. And this sequence may converge to a real number. I mean, it's a sequence just like any other. And we say that it's a sequence, you know, it's a series, which is this sum of n as n ranges from 1 to infinity. It's the limit of these partial sums. That's the only way we can define this rigorously in mathematics, because we can't really say anything about what the actual infinite sum is. But we can talk about at the limit, so that, you know, can you say something that you can get closer to and closer to a point if you're adding these things? So we were looking at ways to ascertain or somehow assess or guess even the convergence or divergence of a series. And convergence means that this partial sum sequence converges to some numbers s. We then say that is the limit of the series, or the series converges to that s. If it doesn't, if the partial sum as a sequence diverges, so it doesn't have a limit, then we say that the series diverges. So the indices in these cases begin with n equal 1, but it doesn't have to be the case. We can start these indices from anywhere we want, 0, 2, 5, 6, so forth. The good thing about this, about this infinite sequence is that we can actually start it anywhere we want and offset the index n then, you know, in those. So for instance, if our sequence is 1/2 to the power of n minus 1, then we can just have it as 1/2 to the power of n and let n start from 0. Not a problem. Or, you know, start from 5 and let the exponent be n minus 5. The same thing can be done, you know, if our sequence series starts with n equal 2 to infinity, 1/n squared, we can change it into some m starting from 1, but this is now m plus 1 because now this starts from 2, this m plus 1. So you can just go back. Just remember that if you're starting from one step before, then the index in the sum must go up. So here, n equals 2. Well, m starts from 1. Then in that, every occurrence of n must be replaced by n plus 1 in those terms. Okay. Then how to evaluate the limits here? Here are some examples of series. The first one, sum of n ranges from 1 to infinity, n over n plus 1. The second one, the sum of minus 1 to the power of n, n ranges from 1 to infinity. And then the sum of n ranges from 1 to infinity, 1/n times n plus 1. So the first sequence, if we just start formulating these partial sums, And we notice that every time we increase this index, S1 is 1/2, the next is 1/2 plus 2/3, then it's 1/2 plus 2/3 plus 3/4, and so forth. In fact, we are always adding a number that is greater than 1/2. In fact, we are adding numbers that are going to grow larger and larger towards the number 1. So this SK, whatever it is, it's greater than 1/2 K for every integer K. Well, larger than or equal to, if K is 1, then it's 1/2. So this SK is actually unbounded, because making this K large enough, we can make this SK as large as we like. And therefore, it's not bounded. It's not bounded, so it diverges. Remember, if it's not bounded, then it diverges. B, well, we have this sum is going to be oscillating between -1 and 0. And in this case, it's bounded, yes, but it doesn't have a limit, because it just flip-flops between 0 and -1. On the C part, 1 over n times n plus 1, we notice that the first one is 1/2, the second one is the 2/3, the third one is 3/4, and so forth. We can actually formulate that the kth element in the partial sum will be k over k plus 1. Well, you don't see it from this pattern. That's a lie, right? You can guess from this pattern, but that's not a proof. A pattern is not a proof. So let's do this. How do we show that that's actually equal to k over k plus 1? Sum of n equal from 1 to k, 1 over n times n plus 1. And that's, we claim that it's k over k plus 1. This is what is claimed, but it's not proven. It says that you can see from this pattern. That will not stand. This, I urge you, never ever do this. When you see a pattern, then you say that, okay, I see from this pattern that this is the formula, and you know, that's what we're going to do, and we're going to just assume that it's so. But never be content with that. Looking at the pattern is a fine way to guess or see what the answer is, but once you do it like this, you still have to prove that it's correct. So first, do it by induction. So first we do the inductive base. K equal 1. Sum as n ranges from 1 to 1, 1 over n times n plus 1 is 1 over 2 is k over k plus 1. So here, this is my inductive base. I formed the inductive base. I notice that if I put in k equal 1, then in fact this sum is going to be k over k plus 1 with k equal 1. 2, inductive hypothesis. So let's do an inductive hypothesis. We assume that when k is smaller than or equal to m, then this holds. Smaller than m for some m. I'm not just doing m. So we assume that for values k smaller than m. So 3 inductive steps. Step. The sum as n is from 1 to m, 1 over n times n plus 1, right? We look at what this is. What is this? We're doing the step now. So what is this? Well, it is the sum as n ranges from 1 to m minus 1, 1 over n plus 1, plus then the very last term, 1 over m times m plus 1, right? So I'm just separating the very last term there. So I make this sum into this. Now it ranges from 1 to m minus 1, and I'm just adding this 1 over m. So now I use the inductive hypothesis for the sum that contains the m minus 1. So I put m minus 1 in place of k in my inductive hypothesis, and I get m minus 1 over m plus 1 over m times m plus 1. So I get this. And here I use the inductive hypothesis, because this sum here by our inductive hypothesis must be, you know, k over k plus 1. Well, I put k m minus 1 in place of k, so I get this and that. All right, and now the rest is left as an exercise. Well, it's not that bad. I just multiply that by m plus 1. I get here m squared minus 1 plus 1 over m I get this. And then, you know, I noticed that if I multiply this out, this becomes m squared plus m. So I just cancel out m. So I get m over m plus 1. And that is what I was supposed to get. I was running out of space for that paper, so I didn't want to write it complete. So I just wanted to show you that you should always do this instead of just doing it with this. When you encounter this explicit formula, you should always check. If not, then prove by induction or something. An important question here is the harmonic sum, harmonic series, which contains the sum as 1 over n. Oh, this is a fascinating thing. I wonder if they have the thing of how do you do this? How do you prove that this is greater than something? This is actually done, not going to go here. It's going to diverge. This harmonic series is going to diverge. I'll show you later a little bit more handy way of showing that it diverges. You can show it here with this technique, but I'm not going to do that now. So let's talk about this theorem of the two series. If we have a convergent series, so the sum as an from 1 to infinity and bn as 1 to infinity, both be convergent series. And then you have the series which has the terms an plus bn, and you add them together, then this is simply the sum of the series limits. Their difference, if you just subtract an from bn and you add these together, then it's going to be the same. If you multiply the number with a constant, then it converges. You can't, however, have a series where you have an times bn and then assume that the sum has, you know, the sum of an times bn is the product of the sum of an plus and times the product, the sum of bn. You cannot just multiply them together. Multiplication doesn't work here. Be careful with that. Here are some examples. I urge you guys to really look at that. So we have convergence series, 1 over n times n plus 1, which we actually showed just now. I used the induction to finalize that proof. And then there is this sum of 1 over 2 to the n minus 1, which is 2. And both of these series converge. You can use these properties. So there is a sum of these elements, and this one element is multiplied by 3 and so forth. So you can verify this. There's an offset here, but it doesn't really matter. You can verify that this is convergent series, and its limit can be obtained, and its limit is 7. You know, I'm not going to go through this. It's just a little bit of an algebraic manipulation. The sum, you separate it into 2 sums, and then this is like just 3 times the sum that we already knew to be 1, and then this is 2, and then it's 1 over 2 to the minus 1s to offset this. So we get 7 as the limit. All right. I'm going to give you a task now to do in groups. I'll put this in pause. Let's resume recording. So we have now discussed this geometric series. So determine whether this series minus 2 over 5 to the power of n minus 1, as the sum ranges from n equal 1 to infinity, converges or diverges. So we should now, by now, recognize this as a geometric series. What is the R in this geometric series? Well, what is the absolute value of that R, and is it smaller than 1? Well, it is. It's minus 2 over 5. So it's definitely smaller than 1 in its absolute value. So this will converge. And easy convergence is just as 1 over 1 minus 2 over 5. So that would be 1 over 1 plus 2 over 5. So that would be 1 over 3 over 5. So that would be, no, not 3 over 5. It's plus. So it's 7 over 5. So that's 5 over 7. That's the sum. It's 5 over 7. Fairly easy. So there are ways to apply these geometric series. So one way to do this, is that you can have repeated decimals as factors and so forth. You can always write them in infinite series. I don't think this is a very nice application. I honestly can't say that I really enjoy this. But what the nice thing about this is, of course, you can sometimes write it in an infinite sequence with a series, and then if you can do that and you've got this repeating sequence, then you can always transform it into geometric series that actually has a rational solution. The thing is, if you have a repeating sequence like this, where there's some numbers sequence that repeats itself, you can always express this as a series where this 1 over 10 to the power of the number of, let's say if it's k digits, then it's k times n, and then on the numerator there is that sequence which repeats, and then you can formulate this into a repeating sequence, and then you can formulate the geometric sum that is equal to this repeated sequence, and then you can come up with the rational number that is that is the sequence, so that the quotient or the reciprocal, the division of integers that is in fact the fraction of integers that in fact is the same number. I'm not going to use there all that much. We talked about the Koch snowflake, which was repeatedly or recursively defined as follows. So recall that we had this. This is actually a nice example in this case. So the first F0 is a triangle. And then at every iteration, F1, F2, F3, so forth, we cut one of these sides of the triangle and we make it into a star. So we remove the middle third of the side and replace it with an equilateral triangle pointing outwards. So what happens here? What's going on here? What's going on here? We need to find out how much new volume is added at every step of the way, or not volume, area. So if we have the area of the first triangle, what is the area of those three added triangles, and what is the area of these triangles, and so forth. So if we have the number of sides in each of these figures, and each side has this length f of n. And the first one, let's say that all sides are length L0, which is equal to 1. So this is an equilateral triangle, all with sides equal to 1. Right? So the next one will have each of those sides turn into 4 different sides. So this side becomes 4. You know, there's 1, 2, 3, 4. There are 3 of them, so n1 is 4 times 3. But the length of each of these segments is now 1/3 of these 1/3 of these original ones. So this is 1/3 of the original, this is 1/3. So there are 4 of them. We are finding the length of that. So in fact, the next one is always 4/3 larger. So look, 1/3 is the length. The number of these edges is 4 times the previous one. So in fact, the length is lengthened by a factor of 4/3. All right, here are the lengths. They always become divided by 4. Sorry, divided by 3. And the numbers become multiplied by 4. So here the number of sides. So the length is 3 times 4/3 to the power of n. Okay, it's not a surprising thing. And you see that this converges. Diverges, because this is a geometric series where this 4/3 is the r, and it's greater than 1, so it diverges. The perimeter length is infinite. But what about the area? So basically what we are adding here is a new triangle, 3 new triangles. But how much area is added? What is the area of this triangle? Well, it's diminished in all directions by a factor of 1/3, isn't it? And because it's diminished in all dimensions by a factor of 1/3, then the added area into the next one is 1/3 to the power of 2, right? Its height and width are both diminished by a factor of 1/3 for each of these triangles. So each new triangle is 1/3 to the power of 2. Mhm. So that's the new triangle. The added area is 1/9 to the power of n. So it's 1/9 times the previous one. So we are just keeping adding this 1/9 to the power of n. So we have a geometric sequence here. And it just goes on and on. But here in the geometric sequence, the inner expression here is going to be 4/9. And we can find the limit of that area at 2 times the square root of 3/5. So this is an example of a situation where we have a curve or a figure who has an infinite perimeter, but a finite area. Well, this is not surprising. It just squiggles a lot, so it's not that. All right. Okay, that's a fascinating thing. You go through these numbers and crunch them if you like. It's actually a fascinating thing. These kind of things appear in mathematics all over the place, so it's perfectly fine. Another thing that may happen sometimes is called what is called a telescoping sequence. And what happens here, there's actually a typo there. There should be a minus there. So if you do this summed up fraction, this 1/n plus n times n plus 1, and you do the partial fractions, which we learned to do when we were doing the integrals, then this 1/n times n plus 1 is in fact 1/n minus 1/n plus 1. And then when you start adding these terms, and again, I notice that there is a typo. This should be minus. And this results in what we can say is what is called a telescoping sequence. So we notice that 1 plus, well, what is here? This and that actually do not cancel out, because there should be a minus. It should actually cancel out. And then this minus 1/3 and this 1/3 cancel out. And then the next one and the next one. And when you add k of these, then only the last reciprocal here remains. So what happens is that the sum starts with 1 minus 1/2, then 1 minus 1/3, then 1 minus 1/4, and so forth. And the kth term is always 1 minus 1/k plus 1. And, you know, as k goes towards infinity, then this just approaches 1. So this situation is known as a telescoping sequence. If you can actually transform it into this situation where when you add more terms, then the stuff in the middle just disappears, then it will be sometimes very easy to calculate the sum of the sequence. So you just have the last one, b1 minus bk plus 1. And if this b sequence converges towards some number, then it's just b1 minus that limit. And if that goes towards 0, then it's just b1. So if you can come up with a telescoping sequence, then that will be fairly easy to gauge. Here's another example of a telescope. I'm not going to go through this. I don't want you to learn this too much. I mean, of course I want you to learn this, but I don't want to use too much time on learning this. I'll put a couple of telescoping sequences in the exercises, but you know, you can figure it out by looking at these examples. Just skip that now. Right. Here's the one thing that I want to discuss today, and this is called divergence and the integral test. Well, one thing that you gotta understand is that this infinite sums and integrals sometimes we can sometimes help use integrals to help figure out what's going on with the sum. That's not really, I mean, it's not necessarily going to give a straight answer, but sometimes we can get a limit there. So for the series to converge, we can transform this into a sequence so that for this convergence well, let's go back. So the idea in the divergence test is there is one thing that must be true, and that is that if the terms that you are adding don't go down towards 0, then it's not going to converge. This is what is known as a necessary condition. So they have to go to 0 for this to converge, but then the terms going to 0 do not guarantee that the sum converges. For instance, 1 over n, we already saw that that doesn't converge, even though 1 over n goes towards 0 as n goes to infinity. But if you say, you know, n over n plus 1, that doesn't go towards 0, it goes towards 1. So if you add those together, then you're not going to have convergence, because you're going to be adding stuff that is never approaching 0. So one way to test for divergence, first test to test for divergence, is see that do the elements go towards 0. If the limit is not 0, or the limit doesn't exist, then the series diverges. The converse is not true, of course. Limit of 1 over n when n goes towards not 0. There is a lot of typos, by the way, in this book. See there, n goes to 0. That's not what happens. N goes to infinity, 1 over n is 0. Terribly many typos in this book. But the harmonic series diverges nevertheless. So these kind of diverging series where the elements go towards 0, those are the ones that we look at. And we want to figure out whether they actually diverge or converge. Well, here's one. Obviously here, n over n minus 3n minus 1, this approaches 1 over 3, and it's not going to be 0, so it's going to diverge. 1 over n to the 3, well, 1 over n to the 3 goes towards 0 as n goes towards infinity. So this is inconclusive. It may or may not converge. It's inconclusive. Well, it will converge, but that test doesn't say it. E to the 1 over n squared, it goes to, n approaches infinity. 1 over n squared goes towards 0. E to the 0 goes towards 1. This diverges. What does the convergence test tell us about the series n is 1 from 1 to infinity cosine of 1 over n squared? Can someone tell me what it says if we apply the divergence test to this? Okay? No? Okay?
I'm not sure, like, if that goes to infinity, maybe that would go to 0. Yeah. And then that would go to 1.
Yeah. So what does that tell you? If cosine of 1 over n squared goes towards 1, right?
Yeah.
It goes to 0. So divergence test says that if the limit is not 0, well, is 1 equal to 0?
No.
No. And therefore, it is not going to converge. It is divergence.
Oh, I see.
The term is going to be closer and closer to 1. You're adding numbers that are very close to 1, and you're taking infinitely many of them. Then obviously you're going to have a very, very, very big number that is going towards infinity the more you take them. Here I want to talk about the integral test. And this is something that I want you guys to just understand. So let me just draw a picture of this. Is there a picture? Yes, there is a picture. Okay, so I don't have to draw it. So think about this. Let's say, look at the harmonic series. And this is a nice, actually a nice situation. Looking at the harmonic series. So the harmonic series, you can think of adding these blocks together, right? So you add 1, 1/2, 1/3, 1/4, 1/5, and so forth. So you can draw this curve 1 over x, and then you look at this region that is left under this, now I can use the notation. So we look at this region here that is under the curve here. So that region, well, let's look at that region. And that region is definitely, its area is going to be smaller than or equal to the integral of 1 over x from 1 to whatever n we are looking for, right? And the sum of 1 over x from 1 to infinity will be slightly bigger than this integral, right? So when we calculate this integral, and we notice that that integral results in the logarithm of x, and as x grows towards infinity, then you know that means that the sum is going to not be bounded, right? The logarithm does grow slowly, but it does go towards infinity as x grows to infinity. And there's a funny thing. You can actually see that this sum as n ranges from 1 to 1 over n. It's actually very close to the logarithm. If you take this sum from 1 to k, 1 over n, it's actually surprisingly close to the natural logarithm of k. And I'm going to leave you to think about why that is. I'll prove it to you later. Well, it's going to be between the logarithm of k plus 1 and the logarithm of k, this here. So it's actually squeezed pretty tight, the logarithm of k and the logarithm of k plus 1. And this sum is between those if you just take it from 1 to k. Sorry about that terrible drawing. All right. Here's another figure. Let's take 1 over n squared. If we take 1 over n squared, we can do the same figure here. We have a similar thing, but we are calculating these. So we're integrating from here all the way to infinity. So we see that the area under the curve is an upper approximation to this the area of these blocks. And if we calculate this, so this is, here it is. So we're adding from 1 to 1 over k, 1 over k, 1 over n squared, where n goes from 1 to k. So it's smaller than or equal to 1 plus, I mean, I'm thinking 1, this is 1, this is not included, plus then the integral from here to wherever we want to go. It's always above those blocks. So it's integral from 1 to k, 1 over x squared dx. So this is the this is more than that sum. But then if you calculate this integral here, then you get 1 over x, and as you know, from 1 to k, that's 1 minus 1 over k plus 1, that's 2 minus 1 over k, so it's less than 2. And as k grows towards infinity, this approaches 2. So it has an upper limit at 2. So the area, whatever that sum is, it's not ever going to be more than 2. It's actually going to be somewhat less than 2, but never mind that. This is just an approximation. So the series as 1 over n squared, n ranges from 1 to infinity, it will converge. And this is all known as the superharmonic series. So we have the harmonic series and so forth. But never mind that. If we have this f of n, which can describe an, and the following three conditions are satisfied. If f is continuous, f is decreasing, and f of n is equal to a of n for all integers from that are greater than or equal to some n, then if we can compare the convergence or divergence of the sum and the integral. And if one converges, the other converges. If one diverges, the other diverges. So this is known as the integral test. Sometimes it's easier for us to compute the integral of the function that describes the nth element than it is to figure out how what the limit of the sum is. The integral test will give us a far nicer way to solve this. Obviously, in this integral test, we have to take this as a limit. We'll talk about that on Tuesday, how we apply this integral to infinity. What we do is we calculate the integral from n to some number, let's say y, and then we look at the limit as y approaches infinity. But we'll look at that more closely on Tuesday, how to do that. If you know how to do that, then that's fine. Here's an example. There are some integral tests, 1 over the square root. I mean, the 1 over the square root, when we do the integral there, we notice that it becomes 1 over square root. It's something, the square root. And then as this b goes towards infinity, we in fact get the square root of 2b minus 1. And then the square root function goes to infinity as whatever that you take the square root of goes towards infinity. So that diverges. Here are examples of series that you can use to determine. You can do this to use the integral test. I'm actually going to do that with you now. So use the integral test to figure out whether this is, punch that, I mean, do this the quick and dirty way. Just punch that function into Wolfram Alpha or some software, check its integral function and see what happens to that integral function. They take the undefined, take the indefinite integral of x over 3x squared plus 1. What do you get? Is it something that when x goes towards infinity, does it go towards some finite number or some infinite number? So I'm going to recreate the rooms now because there are now less of you. Do that in your group and we reconvene in 6 minutes and we discuss. Do the integral test for this 5.13. Use software if you want to. You can do it by hand if you have time, but if I give you 6 minutes, then it's probably not enough. resume recording. So when you are adding elements you're adding terms of the form 1 over n to the power of p, then this is called the p series. The p series, similar in power series, in the geometric series, that by looking at p, we can determine whether it converges or diverges. Well, if p is less than 0, then fairly obviously it diverges because you are adding numbers that are greater than 1. It's not even go towards 0 by the use of the divergence test. If p equals 1, this is the harmonic series, and we can, and for general, if p is greater than 0, we can use the integral test. So we know that both the sum as n ranges from 1 to infinity, 1 over n to the p, this p series, and then the integral of 1 over x to the power of p, they both either diverge or both converge. And if we calculate this integral, assuming that p is not equal to 1, then we can use the power law and we get 1 over 1 minus p times x to the power of 1 minus p. And now if we let this b go towards infinity, we get 1 over p times b to the power of 1 minus p 1 minus 1. And we see that if p is greater than 1, then this goes towards 0. And if p is smaller than 1, then it goes to infinity. On the other hand, if p is equal to 1, we know that it diverges because it's the harmonic series. We already saw that in 2 ways. So the p series converges if p is greater than 0. It converges greater than 1, and it diverges if p is smaller than 1 or equal to 1. Here are several ways of testing. Well, you see immediately here, this p is 4, converges. P is 2 over 3, diverges. N to the power of 5 over 4 will converge because 5 over 4 is greater than 1. Here is a way of estimating from the integral test, so that you can estimate using the integrals, and you may want to figure out how good an approximation that integral is. And if we have the capital N partial sum of this, it doesn't matter what partial sum we have. If we take the remainder of that as the integral, so basically this integral here from n plus 1 to infinity fx dx, it kind of approximates the remainder of the sum. So we have the first capital N terms, and then the rest of the sum is approximated by this integral. Then if we start this integral from n plus 1, we get something that is going to be smaller than this sum, assuming that this f of n is decreasing and f of n is a n for all integers. And if we start the integral from n instead of n plus 1, then we have an over approximation, in which case, it's between these two numbers. So this is actually a pretty powerful tool for figuring out. Sometimes this integral is fairly easy to calculate. Then we can approximate, and we can sometimes get pretty good idea of what the limit is if we have some partial sum and then we have this integrals. So if we calculate the partial sum, we can say that the partial sum is an approximation of the original sum, and it has an error factor Rn. which is between the integral from n plus 1 to infinity and n to infinity. So this is known as the remainder estimate. So how much of that total series sum remains after we've added the n, capital N first elements? And it's actually can be approximated with these integrals. This may sometimes become handy. So please be aware of this. I'm not going to have many questions regarding this. One more thing, and then I'll let you guys go. I'll just say one more thing. And these are comparison tests. We don't have time to go through them all, but we will look at them next. I mean, comparison tests work in the following way. We take the terms and we approximate the term as between two numbers. For instance, we have 1 over n squared plus 1. And we have 1 over n squared. And we know that this 1 over n squared plus 1 is more than 0, and it's less than 1 over n squared. Then we know for a fact that this sum of 1 over n squared plus 1 is going to be smaller than the sum over 1n squared. So we know that this is going to converge because it's bounded from above and all the terms are decreasing. Okay, so let's stop here. We'll talk about this. We'll talk about this later on Tuesday, and by Monday I will put the last exercises online, and they are due on the following Tuesday. And these previous ones, these are the reviews you're now doing. You do them on Tuesday, you will receive your last reviews. And then when you submit, I will review the last week's exercises so that you get the points from them based on my reviews. All right. Are there any questions now pertaining to this material that we discussed? If not, then I think we can stop here.